So this is 1 million particles. I'm going to let them loose at some trajectory inside the circle. And what I like about my approach is that you can do basically any number of points, and you can also do any shape as well. So you can do, you can have the particles reflect around basically any shape. The caveat is you need to know a good implicit equation for that shape. Okay, so circle has a nice implicit equation. You know, it's just x squared plus y squared equals 1. You need to have a nice implicit equation for the shape, and then you can reflect your 1 million particles around the shape. So in order to get this code running relatively quickly for like 1 million points, I had to make a series of compromises on accuracy. And that's what I'm about to talk about now. But if that's not something you're interested in, you just want to watch me have a good time bouncing points around various shapes, you can skip ahead to the next section. A group of circular points inside an ellipse. Normally what you would do is, let's say you have some curve, and you would like to have a moving particle reflect across the curve. It like goes here. You would have to compute the tangent line to this curve, and then you would have to compute the angle of incidence, and then set that equal to the angle of reflection. Of course, you would have to do this for every single point. But because there are 1 million points over here, as you can imagine, that's a lot of logic to do for each and every single point. What we really want in this situation is some function we can apply to all of the points simultaneously, you know, some like fast moving function that does not have any like if statements or anything like that in it, that will automatically perform all of the reflections of these 1 million points that we need / desire. So I think I did 2x squared plus 3y squared for this particular ellipse. I think it was 2x squared plus 3y squared equals 6. Now you might notice that if you do 2x squared plus 3y squared equals 5, you'll get a different ellipse. If you were to plot all of these together, you would get what's called a contour plot for this equation. So this is what the curve looks like if you set 2x squared plus 3y squared equal to 2. This is what the curve looks like if you set it equal to 4, and so on and so on and so forth. So you get different ellipses. This ellipse is the one that I want to reflect across. Then you can evaluate this function at any point, and it'll basically tell you the distance. Or it's not really a distance, right? But it's acting as a proxy for the distance. So essentially, I know that any particular point is going to be really close to the ellipse if 2x squared plus 3y squared on that point evaluates really close, 5.9 or something. I know I'm getting close. And if it evaluates to 6.1, I know I went over. If you compute what's called the gradient for this equation, you differentiate it with respect to x and you differentiate it with respect to y. So if you differentiate this equation with respect to x, you'll get 4x. And if you differentiate this equation with respect to y, you'll get 6y. So I'm going to pay attention to this vector 4x comma 6y. This vector will always be perpendicular to the ellipse. This is my ellipse, and this is my point xy. If I compute 4x comma 3y, that will always be normal to the ellipse. So it's off by a little bit, and you can see it be off by a little. You can see these little like bands appearing over here. This is a result of my decision to not reflect across the exact point, but to reflect the point right before it hits. And this causes a series of like very tiny issues. That was my compromise. As a result of that compromise, I was able to get the code to run very, very fast. You know, maybe there's like a quick way to do this as well. I didn't really have the time to come up with it. Maybe one of you geniuses will figure it out for me and get this running even faster. So I used a Python library called Data Shader. What it does is exactly what I've said, is it divides your image into patches, and in parallel it figures out how many points wind up in each patch, and it produces like a rasterized image that you can just display. It does so very, very quickly by utilizing the hardware on your computer in the best way possible. I added noises to when the points like hit the screen. You know, like Homer Simpson says like, "Ow," when he stubs his toe or something, you know, bad happens in his life.
No!
Can you hear that?
No!
I thought it'd be funny if it played like that a million times. Oh no, okay. It's about to make the collision. If you're all ready. Ooh, spooky. I don't know why. I just found this very amusing. There it is, people. 1 million dose. I hope this is worth your time on this fine Wednesday afternoon. Hopefully you can all see. Yeah, you know, it looks like the egg one is holding together fairly well. Uh-oh, what's going on here? So as you can see very quickly, and you know, you can ignore my like weird rounding errors, but you can see very quickly that the egg is showing a bit of chaos. You see that? Dots that start together stay together, I guess is what I'm trying to say in the ellipse. But in the egg, dots that are starting together are not, in fact, staying together. Oh yeah, I ran out of frames for the other one, but you can still see the chaos proceed with this bottom one over here. And over time, it will. Oh, actually, I realize you guys can't see this. Over time, this will actually fill up the entire egg. This is an implicit equation for a heart. But the problem is this equation is actually not that well behaved. The problem is, for example, if you plot this contour at 0, like if you set this equation equal to 0, you get a heart. But if you set it equal to like 0.1, it doesn't look like a heart anymore. So my little trick of like using the nearby reflections would not work on this shape. However, I think there are other interesting implicit equations out there. You guys ready? All that work? So the claim was that this method would work for any implicit equation. We came up with this implicit equation, which is, you know, it's a spicy implicit equation. It's not such a simple one. All right, ready, set, go. Thank you everyone for joining. I'll be streaming again next Wednesday at 1 p.m. Eastern Time. If you'd like to guide the process at all, you can join me there, or you can watch the replay later. Please like, comment, subscribe. I love you all. Peace.